Hello, and thank you for joining us. Today we'll be discussing Bayes' theorem. The purpose of Bayes' theorem is to find a realistic estimate of an event given that another event is occurring simultaneously. In other words, if one knows the probability of an event F and wants to know how that probability will be altered when an event E also occurs, he might use Bayes' theorem to get an accurate estimate of the new probability F given E. In order to find the probability of F given E, one must have information about the probability of F, the probability of E, and the probability of E given F. While it may seem improbable to have such extensive data, often this information can be discovered more easily than the probability of F given E in the real world. To prove Bayes' theorem, we note that the conditional probability states that the probability of F given E is equivalent to the probability of the intersection of E and F divided by the probability of E. And the probability of E given F is equivalent to the probability of the intersection of E and F divided by the probability of F. Thus, through rearranging these equations, we get the probability of F given E equals the probability of F times the probability of E given F over the probability of E. With this, we have a majority of Bayes' theorem, but we must also calculate the probability of E. In a set S, which E is a subset of, E will be the intersection between E and that set, or E equals the intersection of E and S. We then note that the S is made up of the events F and not F. Thus, E equals the union of the intersection of E and F and the intersection of E and not F. We also know that the intersection of E and F and the intersection of E and not F are disjoint, and there is no element which belongs to both sets. As we know, the intersection of E and F equals the probability of F times the probability of E given F, and the intersection of E and not F equals the probability of not F times the probability of E given not F. It follows the probability of E equals the intersection of E and F plus the intersection of E and not F, which equals the probability of F times the probability of E given F plus the probability of not F times the probability of E given not F. Thus we have Bayes' theorem. To demonstrate Bayes' theorem, we have provided an example of where Bayes' theorem may be applied. Say that you have an early morning discrete math class at 9 a.m. and you've slept through your morning alarm and thus do not have time to pick the proper attire for your class. At the foot of your bed lies two mixed piles of laundry. In the pile on the left, 3 t-shirts are clean and 2 are dirty, and in the pile on the right, 4 shirts are dirty and 1 is clean. If the likelihood that you will pick from either pile is equivalent, what is the probability that you have selected a shirt from the first pile if you picked a dirty shirt? In this typical scenario, we are looking to find the probability that we picked a t-shirt from the first pile given the unfortunate information that we have picked a dirty t-shirt. Thus, in this case, F is the event that we have picked a shirt from the first pile, and the probability of F is the probability that we have picked from the first pile, which is 1/2. The probability we have picked from the second pile is probability of not F is also 1/2. We also know the probability of E given F, or the probability we have selected a dirty shirt from the first pile, is 2/5. We know this because if 2 shirts are dirty in the first pile and there are a total of 5 shirts, then 2 out of 5 are dirty. We also know that the probability a dirty shirt was picked from the second pile, or probability of E given not F, is 4/5. 4 shirts are dirty and 1 is clean, making a total of 5 shirts in the second pile. With all of this information, we can apply Bayes' theorem to attempt to find the likelihood that we have picked a shirt from the first pile. By inserting all of the relevant information into the Bayes' theorem equation, we have 2/5 times 1/2 over 2/5 times 1/2 plus 4/5 times 1/2, which is roughly 33%. We now have discovered that there is about a 1/3 chance that we have selected our shirt from the first pile. Now let's say you want a near guarantee that you were wearing a clean shirt because the girl you have a crush on in your 203 class was mortified by your shirt's stench. In order to find a clean shirt, we must use the Bayesian spam filter method. While this method is often used to determine the difference between a spam email and typical email, in this case we will use the method to determine the likelihood of selecting a clean shirt from your 2 piles. Say that once again you are faced with the dirty shirt conflict. However, this time your unwillingness to sort your clothes has increased the size of the two piles, and they have formed into one massive pile of clean and dirty shirts. You are equally likely to pick out a dirty shirt and a clean shirt from this pile, but this time to filter your clothes, you will smell the shirt. As the various scents of your clothes have brewed in your laundry pile, you reason that if your shirt smells clean, the probability that it is clean is 85%, and if the shirt smells dirty, the probability that it is clean is 30%. Estimate the probability that the t-shirt you pick is clean. If the threshold is above 90%, you will wear a t-shirt to class. If not, you will not take the chance, and you will wear your uncomfortable but clean collared shirt. In this problem, the probability of F, the shirt is clean, and the probability of not F are both 50% again, and it is the likelihood of choosing between clean shirt and dirty shirt, the probability of E given F. The probability a shirt is clean given it smells clean is 85%, and the probability of E given not F, the probability a shirt is clean given it smells dirty, is 30%. Plugging these in, we have 0.85 times 0.5 over 0.85 times 0.5 plus 0.3 times 0.5, which is roughly 73%. Thus, through using your knowledge in 203, you have figured out that the probability of getting a clean shirt is 73%, and decided it is best not to take the risk of picking a t-shirt, instead wearing your collared shirt. You also didn't scare off your crush due to putrid stench. Way to go! One can see that in the same way this method helped sort good shirts from bad shirts, it could also be used to sort through spam. The last important use of the Bayes theorem that we will talk about is the generalizing Bayes theorem. This theorem states that in the event that an event F and not F are mutually exclusive and cover an entire sample space, we can have the Bayes theorem extend so that it can take these various probabilities into account. In the case that you have mutually exclusive events that add up to the probability of your sample space, you take each additional event into account by taking the summation from 1 to n of the various probabilities of the F events multiplied by the respective probabilities of E given F. So in the case of smelly t-shirts, our sample space is dirty and not dirty t-shirts. An additional mutually exclusive event might have been the selection clean collared shirts in addition to the selection of clean t-shirts and dirty ones. In the case that there was equal chance that we picked either a dirty t-shirt, a clean t-shirt, or a collared shirt. For more videos on discrete mathematics, please visit www.noatom.com.